Mac is a physics educator and researcher specializing in physics education research at the University of Maine. His work focuses on developing research-based instructional materials for undergraduate and K-12 education. He explores TA and teacher assessment skills, professional development, and student understanding of concepts like electric circuits, and mechanical waves. Recently, he has led studies on student learning in analog electronics, developing instructional materials for upper division lab courses. Oh, Mac, I wish you were there when I was taking physics. It would have been a lot easier for me. Mac's pop culture reference or go-to, at least tonight, was the Hidden Brain podcast.
All right. Okay, so I'm super excited. I'm going to start this by saying that I'm going to focus on an observation that led to total confusion on my part, on the part of my collaborators, and this might not inspire confidence in this presentation, but I think this is what leads to really exciting research. Okay, so what we found is that after research-based instruction, which has been shown to improve student conceptual understanding of physics, we find that student performance on two questions focused on the very same concept can vary dramatically. On one question, your students answer it, they do really well, you pat yourself on the back as an instructor, and then you administer another question that to you feel like it's asking the exact same thing, requires the same reasoning, and your students struggle. And we were thinking, wow, after all this work, what's going on in this second case? Okay, well, let me just say that this perplexing observation led to 10 years of research. It's still going on with my wonderful collaborators, all of whom are shown there. Okay, to set the stage, I want you to answer a question, and I want you to shout out your answer as soon as you can. Okay, are you ready? Okay. A bat and a ball cost $1.10 in total. The bat costs $1 more than the ball. How much does the ball cost? Okay, I'm hearing a lot of different things. But I will say that the one that I'm hearing quickest is 10 cents. That's certainly how I answered that initially. Because you think, well, the ball costs 10 cents, the bat costs $1.10, but then you see it adds up to $1.20. So we recognize that no, the ball must cost 5 cents, and thus the bat $1.05, and together it's $1.10. The reason I'm focusing on this is because this outcome, the fact that so many of us say 10 cents initially, is due to the nature of this question. There's something going on that cognitive scientists have identified as a salient distracting feature, where we're told it's $1.10 in total, but the bat costs $1 more, so you subtract them and say 10 cents, although you could have easily spent more time and figured out that it was 5 cents. This is what we think is going on for our physics students. Basically, we believe that these kinds of inconsistencies in performance that we're seeing are due to the way our brain works, not so much to whether they understand physics or not. And so we've turned to dual process theories of reasoning that popularized by Daniel Kahneman in Thinking Fast and Slow, which model reasoning as consisting of two processes. Process one, which is fast, automatic. It's not conscious, you can't turn it off, but it's informed by your prior knowledge, your beliefs, your goals, as well as contextual cues in, for example, a question. And then there's process two, which is slow, deliberate, and effortful. In general, humans are cognitive misers. We prefer not to do this, and most of our daily life is process one, thankfully. However, we want our physics students to engage in process two on a lot of our questions. So in order to study this, what we've done is we've paired questions where we have a question that probes whether or not students demonstrate the requisite knowledge and skills or mindware with a question that sees if they can apply that mindware in an analogous situation. And as you can imagine, we're obsessed with students who can answer the screening question correctly, but answer the target question incorrectly. So I'm going to do a little bit of physics here. Here's our screening question. We ask at which of the three labeled times is the speed of the car the greatest? This is a position or x versus time t graph. And basically, for speed, we need to think about velocity, a change in position over a change in time. So if you look at identical time intervals, the biggest change in position will tell us where the speed is the greatest because velocity is the slope. So that's point A. Students do this time A. Students do this really well. However, if we give them this graph with two cars and ask when the speed is the same, students struggle. Only 2/3 answer this correctly, and they tend to focus on that intersection, which again is a salient distracting feature. All right, so what we did is we asked students, what did you notice first when you had responded to this question? This student said, initially, I thought that when they intersected was going to be the point at which the velocities were the same. Initially, I thought the answer would be B, simply because the graphs were intersecting. The point where the lines intersected seemed to stand out to me. So this suggests that it is, in fact, salient. And more importantly, out of those students who had the knowledge and skills to answer this question, nearly half reported that they focused on that intersection. So this just really reminds us that process one serves as the entry point into any reasoning path. So as a result, whatever model is triggered, you have to deal with that in your reasoning. And so we've realized that we need to support our students in analyzing and scrutinizing these ideas from process one in order for them to be successful. In many cases, they have the relevant physics, they're just not able to access it. Thank you.
Question one, why are the microphones this height? And no, sorry. No, my actual question is, so as like societally, we put a lot of like stock in things like Jeopardy, where you're answering questions like really quickly. And we kind of like growing up, train yourself to like answer things quickly. So are you looking at sort of like activities and things that you can do as like training, sort of to train brains before you administer these tests?
So that's a great question, because I think that is one of the problems that our students are struggling with. Is often they're told, you know, you've got to go with your gut answer on a timed test, you have to respond quickly. All the rewards are for that, and what we're trying to do is make them think, okay, and we've come up with strategies for doing this where we can kind of slow them down and have them reflect on their own process. For example, even asking this question, that's enough that if we then give them another opportunity to answer it, they will change their thinking. So we're really trying to get them to be critical. Obviously, we don't want to get them to the point where they never trust the first response, because, I mean, most of our daily life, we're kind of automatic, and that's how we've survived as a species. However, yeah, we are trying to get them to be a little bit more reflective and metacognitive.
Should students be given the equation and the laws for the exam, or do you feel like they need to memorize them and then apply them on the exam?
That is a great question. I will say personally, I feel like if they just need to remember a formula to answer my exam question, it might not be really getting at what I want, in the sense of I want them to be able to recognize the need to use that. So I don't feel as strongly about memorizing. I know in our courses, we actually provide those equations, and students still will often struggle because they don't recognize the need to apply it and they don't understand how it applies to the question.
I wish you were around in the early 1980s.
I recall back sometime in the late 1980s, there was a psychologist that researched the 7 centers of intelligence, realizing through that research that there's a multiplicity of modes that we get our information and learn by. Visually, talking, lecture, books, and we all don't have a whole bag of that. We all have different aspects of that. How does that play into this, do you think?
Well, okay, so what you're raising is really interesting here, because we do know that, I mean, most good instruction uses a variety of, you know, representations, text, etc. But the thing is, in terms of thinking about process one, often it's cued by things that are particularly salient. That could be text for some students, that could be an image. I mean, that feels like a rich thing to study. For example, what would happen if we removed the image and just described it in text? In a lot of our physics questions, we have an image, and then we have text describing it right next to it. And so people are doing eye tracking studies to figure out what students are actually attending to. So that could perhaps answer some of that. But, you know, there are so many different things going on. So that's a little bit beyond the scope.
Have you shared this process with students and seen its impact?
Okay, yes, we do this. We do talk about dual process theories of reasoning probably in the second week of the course. My colleagues also did a controlled study where some sections had the instructor, every time students were asked a question in class, you know, they would have them think about, well, did this come to your mind immediately, or, you know, is this connected to physics, etc. We didn't find that that was having an impact itself, but we believe that the more scaffolded things we've been doing recently, that can actually shift how students are reasoning. So I would argue probably some combination of those two would be the best.
after you tell students about the two processes, is there any work that you've done to see if working in groups for students sort of helps them steer more towards process the two that you want them to go towards?
That's interesting because that's a hard thing for us to do because we have so much group work in our courses, because all the research has shown that, collaborating, essentially one person, the group of people function as one person, and so metacognition or internal thought is regulated by the different people. So some research studies we actually focus on that. But we haven't done that explicitly. But I will say some of our most effective existing research-based materials, often they do rely on those groups discussing, or they have hypothetical students that articulate different lines of reasoning and the students need to think about. So I do think that goes hand in hand. And we hope to kind of incorporate these sorts of activities into our tutorial materials.
Very quick question. Was it the question?
Mac will be out in the lobby afterwards or at the reception.